So here's the answer for the decision tree for the diabetes dataset, and I just added some features so you can have a sort of review on Python programming. So first, no, for the decision tree, again, import numpy, panda, matplotlib. Then I'm gonna read the diabetes dataset. This is the first 10 elements, and if I will look at the shape, there are 768 rows and 9 features. As you can see here, pregnancies, glucose, blood pressure, skin, and the outcome, or whether that person will have a diabetes or not. So true, 1, then 0, false. Okay? So these are the features. Then this is not necessary for answering it. Here I have here the correlation. I'm just looking at the correlation of the various features. So I just added this seaborne heat map, no, for plotting rectangular data as colored encoded matrix, and I'm just looking at the correlation matrix for the diabetes dataset. So here, the name of my data frame is diabetes underscore df for the data frame. Now, the .core function is from pandas, used to find pairwise correlation of all columns in the data frame. It works only for numeric values. It ignores non-numeric. So if we look at the correlation, I'm just going to show you the output here. By the way, this one, print equal 100 times, just to distinguish it with the correlation matrix. To use another color for the correlation matrix, you can use the yellow, green, blue. I like this one, the yellow, green, blue. And then if you want to add the actual correlation value, you can actually use this one. You just put annotation to be true. Okay, so you will see here the correlation value aside from just the intensity of the color. So I prefer that. But if you just want to show the correlation values, which actually is just values from 1 to -1, which signifies the intensity of the correlation for each feature, you will see it here, how they are related. Then we're going to inspect how many from this one, from the outcome, is, sorry, the outcome values. When you look at the head from the outcome, how many are positive, how many are negative. So I just want to show you, no, how to count the number of rows with negative values and positive values. So simply the name of the data frame dot location, and then diabetes outcome is equal to 0, and the diabetes outcome equal to 1. I placed it in count 0, count 1 variables. Then in Python, you can just say here outcome 0, 1, colon, open parenthesis, then the value of count, comma, comma, enclosed in single quote, then comma, the count, and so on. So you see here, there are 500 negative and then 268 that is positive. Now let's make the decision tree. I want to make this bold, so just enclose it in double asterisk to make it bold. So remember, if we're going to make the decision tree, we have to get the features, and then this is the x is the features, so minus the last part, which is the outcomes. So index location minus the last index for the column, last column index. You would see here it does not have the outcome column anymore. And then of course the diabetes is the outcome part is our y. So you can see here, I will just show you the a review also to get the last values. You have the tail, last 10 elements, and then as usual you have the training set, test set. So don't forget to train underscore test split, and 80/20, 80 for training, 20 for test. Then basically a lot of you did this. You just have the Gini index, then D3 model fit extend. So just run this, and same what's before. You just use the export graph base, then the normal file extension for graph base, the dot, that's the standard. Then using the OpenCV for image processing, it will output something like this. Okay, now what if you want it to be, okay, let me run, and run. So you will see that it's a very big decision tree, and you will not be able to clearly see it. So best way to do that is to simply just show us the depth up to 3. So when you specify the max depth to be 3, when you output, you will see that it's up to 3. So 0, 1, 2, and 3. Now when we look at the, by the way, it's okay that you just simply made the decision tree right away given the data set. Anyway, the values are all continuous. But I want to discuss on the pre-processing part. No? So let's take a look at our data set. When you look at our data set in the data frame, you would see here some values. For example, skin thickness is 0, insulin 0, 0. In these rows, there are no values for insulin, no values for skin thickness. So it's possible that some have no values, and with this, I wanted to check how many are missing values. How many rows does, for example, it can have missing values for glucose, blood pressure, and so on. So in this case, I just have here the format. I just also want to show you that it's also possible that instead of the comma, you put right away the values, just what I did here in the count part. It's also possible to identify index in outputting index through the format. So just specify this is the first index. So in this case, that format, the length of our data frame, and in this case, the total rows. Then I want to count how many in every column is equal to 0. So I did not include pregnancies because in diabetes, it's also possible that if it's male or female, because it doesn't specify, it's not okay that a male will get pregnant, right? So I just left the pregnancy part, just focus on the glucose, blood pressure, skin thickness, insulin, and so on, except also for the outcome. So I have here that there are some missing values for glucose, blood pressure, skin thickness, and so on. Then what strategy are you going to use if they're missing? So I have here, I am removing the, in our first part, for our data frame, I'll show you, because I'm going to use imputer, I will not include pregnancy and I will not include outcome. I will use this simple imputer that will remove, or I will put values to those with 0. So in this case, I'm making another data frame from our diabetes data frame in the index location, which is our start column to our end column. Then here, glucose only up to age. This is the diabetes data frame for imputer. Okay. Next, I'm gonna use the simple imputer. Previously, it's just imputer, but now it's changed to sklearn.impute. And the strategy that I'm gonna apply is, if there are missing values, it's 0, I will just use the mean. Right? Then I will fit it to the imputer. Then afterwards, we have transform. So I will look at it. There are 768 rows, and there are now 7 columns. We're working on the 7 columns. Then afterwards, I'm going to add back the pregnancy column and the outcome column in our data frame. So to output the pregnancy column, we just say here diabetes from the previous data frame, index location 0, 1. This is the pregnancy column. I'll just show you that. I'll remove this so you will see that this is the pregnancy column. Okay, this is the pregnancy column. So I'm just indicating that this is the index 0, okay, up to 1. This is the first index. Then I'll show you the how to output the outcome column from our original data frame. So from 8 up to the end. Next, I will convert the diabetes data frame for imputation imputed into diabetes impute, and then I'll just get the head. Okay. Now when you transform, which is the output of this diabetes underscore df or data frame imputed, there's no column names in the transformation, because here we fit and then transformed it to diabetes df imputed. So I need to insert first, no? Insert the pregnancy and the outcome. So basically when I insert, if I look at the head now, show you, this is the pregnancy and this is the outcome. Okay, then afterwards I'm going to simply get the columns of the original one, diabetes df, that columns, to the diabetes imputed that columns. So this time if I run this, you will see from this preg 0, 1, 2, 3 up to 6 to 8 to out, it will now return with the pregnancy glucose, because this is important in making the decision tree for labeling purposes. So this is now the diabetes imputed, and this is our original diabetes data frame. So you can see it's already imputed, because if you look at here, insulin is 0, 0, 0. It was now changed to 155, 155, meaning this is the mean for all insulin values. And for skin, number 2, row 2, so you can look at here, row 2, 29.15.15342. This is the mean for the skin thickness. Okay, and then let's do the training once again for the diabetes. The X features, this X represents the feature, this is capital X, and Y represents for the outcome, the one that we're going to check. So X, this is X, okay, pregnancies to age, and then we have to remove the outcome value, and this is the Y, which is now holding the Y, the dependent variable. Then let's have the train test split. In this train test split, we have 80-20. The test set is just 20%. And we're still using the Gini for model. I just named this now D3 underscore model. And still max depth now is 3. If I run this, okay, I'm gonna show you another way of outputting the tree using the subplots. The same with the iris dataset. You can use this, just the tree plot tree. Just don't forget to import tree and then D3 model. I'm using the D3 model. Then if you output this, see it's colorful. And then now this time, let us predict, no? Let's check the prediction and the accuracy of our model using the confusion matrix. And let's look at the accuracy and the actual report. So here, in the confusion matrix, it's 84. This is the true positive. And then this is the negative. But there are 84 true positive. And then there were 15 that were categorized positive but actually negative. And this is the categorized as positive but actually negative. And this one is categorized as true negative. Okay, that's the confusion matrix. I appended here confusion matrix just in case you forget that the actual is on the upper part, actual positive, actual negative, then it's the true positive, and then the true negative. So the good thing here is it's 84 and this is 36. So if you add them, we get 120. 84 plus 36, those are the correct classification. And 15 plus 19, those are the incorrect classification. So our accuracy is 77.92%. Now, precision, you can see here for the negative is 82% and the positive is 71%. Now, precision is actually calculated as true positive over true positive plus false negative. And then for recall, it's on the true positive over true positive plus false negative. So that's it for our decision tree.